So if we look at this stuff here, here's what we know. Kirchhoff's laws are the basis of all circuit calculations. I don't care whether we're talking AC or DC. It doesn't really matter. They're the basis. So, and it turns out that Kirchhoff's laws is the worst possible way to actually solve a problem. So if you're going to try to solve a problem and you're in this chapter and you're going after Kirchhoff's law, one, that means you're typically desperate and you're just going to go for systems of equations. This chapter is learning how to see series and parallel. What we want to do here is that when we look at these Kirchhoff's laws, the basis for them is really two very deep laws. One, KCL follows the law of conservation of charge. That means that charge coming into a node must be equal to the charge coming out of the node. You can't create or destroy charge. So therefore, the current coming in must be the current coming out. KVL follows from the fact that the electric force is a conservative force. And because it's a conservative force, that means when I do work around a closed loop, that work is always zero. And so therefore, since work and potential are connected to each other, we then say here that the sum of the voltages around a closed loop is zero. And we have a sign convention, okay? And I know that the sign convention in physics 4A is just plain screwed. I mean, it's just, why would they teach that sign convention? So let's make it nice and simple, the way real people really calculate it. If you take a path and you see a plus sign, you put a plus. What do they tell you to do in physics 4B? You see a plus, you put a minus sign, okay? I guess you could do whatever you want. And then if your path hits a negative sign, kind of crazy, maybe you should put a negative sign instead of a plus sign. So that's the sign convention that we want to do. And so here we go. Let's go look at the example that we were looking at, and let's go from there. So the first thing that we want to do here is this, that when I look at this thing, we were looking at this example, and we want to determine the power absorbed by each of the resistors in the circuit. So I got 1, 2, 3 resistors. So the way I look at this thing here is that I always pay attention to the sources first. And I say, is there any low-hanging fruit, as they say, right? So we look for elements that are in series with current sources and parallel with voltage sources. So the first thing that I'm looking at is that I'm going to look for the current source first. And if I look for the current source first, you could see that I have one right here. I have a 2 amp source. So if I follow the current through the 2 amp, I can see that it's going like this. But note that as I get to this node right here, then the current splits at this node. And maybe I should label this node A. So at A, the current splits. At B, it splits. So the only thing that I could say here is that because all of these 3 elements, the 2 amp, the 6 volt, and the 4 ohm, are in series, then the current must be the same. So that means the current through the 6 volt source is 2 amps. The current through the 4 ohm resistor is 2 amps. So right away, when I look at the 4 ohm resistor, we could see here is that it's in series with the 2 amp source. So what does that tell me? That tells me that the current of the 4 ohm is then 2 amps, which then tells me if I look at the power of the 4 ohm resistor, since I know the current, I'm going to say that I'm going to go, it's the current of the 4 amp squared times the resistance of the 4 amp. So in this case here, then I could see here that this value is going to be 2 squared times 4. So I got 4 times 4. I'm going to get positive 16 watts. And I now know what the power is of the 4 ohm resistor. Okay. So now let's move on. So now I'm asking, there's only one current source, and then I'm asking the question, is there anything parallel to any of the voltage sources? Well, you could see that the 6-volt source all the way on the left, nothing's parallel to it. When you look at the 8 and the 12 volt in the middle, they're not parallel to any resistors, but they are parallel. But there is a parallel between the 8 volt on the left, the right, and the 8 ohm resistor. So when I'm looking at this thing here, you could see that there's only 2 nodes between these two here. So that means here that when I look at the 8 ohm resistor, maybe I should write out 8 ohm resistor like this to make it a little bit bigger. For the 8 ohm resistor, what we're seeing here is that it's in parallel with the 8 volt source. Well, if it's parallel with the 8 volt source, then this tells me here that the voltage of the 8 ohm must be 8 volts. But if it's 8 volts, then I could go in and calculate the power of the 8 ohm, because that's going to be the voltage of the 8 ohm divided by the resistance. So if I start to plug that guy in, you're going to see here that I'm going to get 8 squared divided by 8, which then tells me that I'm going to get plus 8 watts for this guy right here. So I now know that. So what that really means here is that I know the polarity of this guy. It's positive and negative. Why? Because the 8 volt is up there and the negative is down. So now what I'm left with is that I'm left with just the 6 ohm resistor. So let's go focus on the 6 ohm resistor now. So note that this is not in series or parallel with anything. And that's typically that you either got to use KVL or KCL. That's typically what you have to do. And that's almost always the sure sign of having to use KVL or KCL. So the thing that we can do here is that we can do one of things here. When I look at this circuit, what you're seeing here is that there's a path with voltages, voltage sources that is. If I try to do the left path, let's see what happens here. If I try to use the left path, so that means I'm going to take a path. Wait, before we get started, we should do one thing here. We need to pick a direction for the polarity of the 6 ohm resistor. Do we know which direction the current's going to go through the 6 ohm resistor? The answer is no. We have no idea. So what happens here is that you start by giving the voltage across the 6 ohm resistor some polarity, and then KVL is going to dictate what's going to happen. And it will tell you whether it's positive or negative. So for the sake of argument, I'm going to imagine that the current is coming here. And for the sake of argument, and also trying to irritate you guys with more sign issues, I'm going to pick this to be positive and that to be negative. So this means here that my 6 ohm voltage has that polarity here. So let's go make a path here. So if I go a path like this to try to get the voltage across the 6 ohm resistor, look what happens here. So I'm going to use the left loop to get the voltage of the 6 ohm. So what happens here? Well, I need to make an assumption about the voltage across the 2 amp source. So if I look at this thing here, I'm going to say that this source is active. Is it active? I don't know the answer to that. So I'm going to do this thing right here. So what you're going to see here is that if I do this, then I'm applying KVL. around the left loop. So here I go. Look at my path. So if I look at my path, look at my direction here. What do I see? I see a negative sign. So that means here I'm going to get minus the voltage of the 2 amp source. And then I'm going to come around this direction and I hit a negative of this guy. And when I hit the negative, I'm going to get what? I'm going to get another negative for the voltage of the 6 volt source. And then I come here, because this is a passive element, we know that the polarity here must be plus and then minus. So then I'm going to get plus the voltage of the 4 ohm resistor. And then I'm going to come all the way around. And you could see here that I'm going to hit what? I'm coming this direction, and you're seeing that I get the negative of the what? Of the 6 ohm resistor. That has to be 0. That is KVL. So let's look at this thing. Do I know the voltage of this guy? Of course I do. It's minus 6 volts. That's the source. Do I know the voltage of the 4 ohm? Yes. Because we know that if we have 2 amps and we have 4 ohms, then according to Ohm's law, this guy should be 8 volts here. And we're trying to find the voltage of the 6 ohm. The question is, do we know the voltage of the 2 amp source? And the answer is no. So this tells us here is that this is an unknown. So what you're seeing here is that this gives me 2 unknowns, one equation, and according to this is not solvable. So I don't do that. So then I'm going to do my other loop here. So the other loop that I want to do here is that I'm going to look at this loop here. So if I look at this loop, note that I can make a loop around here. Now I'm going to pick a direction, whatever direction that I want to pick here. How about if we go to the right? So I'm going to go this way, this way, this way, all the way around. So let's go apply KVL. So now what we're doing here is that, I got to bring this guy down. So what we want to do here is that we're going to take the center loop to get V6 ohm. And of course, we're going to be using KVL. So let's pop this guy down here. So what you're seeing here is that I'm going to label this node here, and I'm going to call this node C. So what am I going to do? I'm going to start at node C and go counterclockwise. So here I go. I hit the negative voltage here. So this is going to be the negative voltage of the 8 ohm. I keep going. Look what I get. I get positive 8 volts from the source. And then I hit what? I hit the negative voltage of the 6 ohm. And then I come all the way down. And then I hit the negative 12 volts. And then I sum that equal to 0. So what do I know here? Well, I know that the 8 volt here is what? 8 volts. I know that this guy's 8. I know that this is what we're looking for. And then I have minus 12 here. So you could see immediately that these guys sum to 0. So what does this tell me here? So now if I solve for V6 ohm, you could see here that I get V6 ohm is minus 12 volts. Wait a minute. That tells me that if I look at this resistor, I defined my polarity here for this guy to be like this, but I'm getting a value now of what? Minus 12 volts. So what did KVL just tell me? It says, oh, the polarity is opposite. So in other words, I can rewrite this guy where this guy is 12 volts that has a polarity like this. This is the direction that we want to go. And so therefore, it's 12 volts with the polarity up and down. So now, if I go calculate the power, so the power, of the 6 ohm, well, I got the voltage, I don't got the current, so then it's the voltage of this guy squared divided by this guy. So then this guy's going to be what? It's going to be 12 squared divided by 6, which then gives me positive 24 watts for the power of the 6 ohm. That's the end of that example. So what I want to do now is that I want to go in and I want to start talking about series and parallel. So now we're at one of the most important pieces in the whole course. Parallel and series equivalence. Man, I know I've already said this, but I cannot stress to you how important this section is. It is just so important. You gotta put in a lot of time into this section. And really the best way that I can really explain this thing goes something like this. And I'm gonna give you an analogy. From time to time in the past, my kids have come up and they give me an algebra question. So when I think about an algebra problem, if I gave you an algebra problem that said, this times this divided by 2 is equal to, let's say, 2x. Now, if you look at this problem, you'd probably say, that's quite simple, right? You can probably do this in your head. And the issue is that you've been so practiced at algebra that you can just look at this and you know exactly what those steps are, right? You can visualize what is actually happening. What I need you to do in this chapter is that you need to look at a complicated series and parallel circuit and immediately know how to break this down. You have to look at, just like this equation, you have to look at that circuit and like this. I want it like that fast. Just like you can take that equation and you can break it down very, very, very quickly, I need you to be able to do that. And guess what? There's only one way to do it. The only way to do it is you got to practice. And let me tell you, my solutions to my homework, I can Google them. Oh yeah, I can Google them and I could go like, yeah, that's my solution right there. I'm gonna let you in on a little secret. I know what people do online. And I promise you, the circuits that you're gonna get from me, they're not online. And when you go look at the grading scheme that I have, the quizzes and the exams, you're not gonna see those circuits. So guess what? You're not gonna have access to the solution. And I can tell you what actually happens. I'll see people sit looking at their quiz and the exams who haven't put their time into it. And you know what they do? They'll sit there for 30 minutes and not be able to write down a single thing. So Just like my kids, if they don't put their time into doing their algebra, they're never going to know how to solve that algebra equation. You do because you put your time into it. That's how I need you to react when I say, I want you to be instantly draw the circuit and immediately be able to realize it. And it takes a lot of patience and it takes a lot of time. So here we go. So the idea here is that what you're going to find here is that in this part of the chapter, we will get complicated circuits. And the idea here is that, one, you have to identify what is in series and then use series techniques to, figure it out. And then you're going to have to identify what's in what in parallel. And once you do that, then you're going to have to use parallel techniques. And what you're going to see here is that this is all about resistor reduction. You have to be able to do resistor reduction so then you know what series technique to use, what parallel technique to use. And so what you do here is that I could use a second analogy here. When you eat a sandwich, do you take the whole sandwich and shove it into your mouth? I'm assuming, well, if you do, I don't want to see you eat for certain. But the fact is that if you're a normal person, you probably take bites from your sandwich, right? You take bites to eat the sandwich. So the same thing happens here. In circuits, what we do is that we break it down into pieces. So when I say bites here, you're going to break the circuit up into pieces. What kind of pieces? Series. What other kind of pieces? Parallel. So you break it piece by piece until you can get the current or voltage of the place that you want to calculate here. So here's what we want to do then. Let's go do it. So what we want to go do is that we want to go in and start to look at this thing. So it goes something like this here. So the main question that we are asking, okay, here's our main question. Is the primary behavior of the circuit series or parallel? Once you know it's series, then there's a list of things that you're going to get that says, okay, this is what it means. This is what I got to do. If it's parallel, then there's a list that you got to go through. And that's what I want to do now. I want you to learn to see series and parallel and move to the next level. And let's go do that. So the first thing that I'm going to focus on is series. Series equivalence. okay? As soon as you identify that the primary behavior of a branch in the circuit is series, then there are essentially 4 characteristics that you got to do, okay? So as soon as one realizes a branch of a circuit is series, there are 4 characteristics. God damn it. Here they are, okay? The first thing here is this. Series resistances add, right? And why do they add? Well, when you look at the resistance equation, okay, so if you look at the resistance equation, tells you that the resistance is the resistivity divided by the length, multiplied by the length divided by the area. And what you're seeing here is that when you add resistors in series, you are increasing in length. So that means here is that by adding resistors in series is equivalent to increasing length. So therefore, R series is then directly proportional to length, and it looks like this. Okay, that's the first one. Series resistances add. So here we go. So the second thing here is that we know that the same current goes through all series elements. So I didn't box this. And so what we're finding here is that what I really mean here is that if I have a circuit that's in series, okay, if I have a current that's in series, then that means I can draw a series circuit like this. So I have resistor 1, resistor 2, resistor 3, and this is my voltage source. So when I look at a node, let's focus on a node. Let's look at this node right here. What we know about this node here is that the current coming in must be the current coming out of that node. And when I look at that node, what you're finding here is that I cannot destroy charge at a node. That would violate conservation of a charge. So now let's look at the resistor. So when current comes in through a resistor here, you cannot destroy charge through a resistor. So what you're finding then, that the current through this resistor, I2, is then going to flow through, and it's going to be exactly at that blue node. And so therefore, the current going through resistor 3 is I3. So if I keep following this around, that means that the current through each of these elements must be the same, and therefore the current of the source must be equal to this guy. Okay, that's what I mean by this here. So if you now look at a series circuit here, what you're finding here is that if I apply KVL, tells me that the source voltage must be the combination of all of these guys. And if it's the combination of all of these guys, I could then write in from Ohm's law, since the currents are all the same, I'll just call them I. And you could see here is that I can factor out the source current here. So therefore, when I look at my circuit here, I can rewrite this thing to say that the source voltage is equal to R series times I source. In other words, my equivalent circuit here can be reduced as one resistor here. So this is 1, 2, 3, and this guy could then be my series here. Now, how do I see this in a circuit? You're never going to get this from me, right? Never, ever, 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 ever. Have some complicated circuit. And you're going to look at this complicated circuit and you're going to look at a piece of it, just like taking the bites out of a sandwich. And what you're going to see here is that I'm going to have a circuit where I have a branch, R1, R2, R3. So now I can take this circuit and I can draw the equivalent here. In other words, if I come over here and I repaste this guy, what you're seeing here is that I could replace this branch here by one resistor R series. And that one resistor, of course, is going to be the equivalent of adding these guys. And what do I know? I know that the current in this branch here, I, for this branch, is going to be the same through each of these resistors here. So now I know about the current in that branch, and I know its resistance in that branch. So now what we want to do here is that we want to go in and we now want to start talking about voltages here. Okay, so we talked about series resistances. We talked about the same current through all series elements. The next thing that we got to talk about here is we got to talk about voltages. And here we go. So 3 here then says this here. God damn it. So 3 says this here. Voltages are divided among series elements. And they're divided in 2 ways. Okay, one way is KVL. So if I look at KVL, what you're going to find here is that the voltage of the branch isn't going to be the voltages, the sum of the voltages in that branch, right? However many that there are. That's one. The other one, which we started looking at the lab here, says that there's something called the voltage divider rule. And the voltage divider rule says that the voltage of the nth resistor is going to be the nth resistor divided by the series resistance divided by the voltage of the branch. Okay, remember, 99% of the time when you have circuits like this, you want to be using voltage divider rule. There is some problems at the end where you're going to have to use KVL and KCL, and you're going to see that that's considerably harder. So let's go look at the voltage divider rule. we can easily derive the voltage divider rule. And so one of the things that we already said here is we said this: if I have a circuit that's series, what we said here is that the current through all of these must be the same. So in other words, if I look at the current, and this is 1, 2, and 3, the current must be the same. But if it's the same, I'm now going to use Ohm's law to write down the voltages. So that means if I look at the voltage across 1, that's got to be V1. So that's got to be this guy right here. But wait a minute, if I look at 2, it's got to be V2 over R2. And you could see that I could just keep going on here. So depending on the number of elements that I have in series, I can write this. But wait a minute, we just said that for a series circuit, I can write down the equivalent of this guy right here, right? But the source current is also equal to what? The source current is also equal to the voltage of the branch divided by the series resistance. So if I rewrite this thing here, right, if I focus on this guy right here, right, if I focus on these, then it tells me here that the voltage of the nth resistor is going to be the nth resistor divided by the series times the branch resistance. And this is the voltage divider rule. So when you look at the voltage divider rule, what is it really telling you here? Well, what you're finding here is this, that it tells us here that the percentage of voltage drop across a series resistor is equal to this thing, Rn over R series. Okay, so it's telling me that the percentage of the voltage drop has to be proportional to the resistor. So this implies here, if I have a larger resistor, I'm going to get what? A larger voltage drop across that resistor. If I have a smaller resistor, then I'm going to have a smaller voltage drop across those guys. So the voltage drop tells us about that. And so that's what the voltage divider rule. But let's go back to KVL and talk about the branch. So one of the things that what I did here is that I was using this circuit right here, and I want to think about a branch. So what I'm seeing here is that I'm looking at the circuit, my series circuit here, right? So I have a series branch, and what you're going to find here is that according to the voltage divider rule is that if I have a voltage drop across this branch, then I could go in and calculate the voltage of each of these resistors without having to look at this rest of the circuit here. I don't have to look at it. So what this really means here is that I can also replace this circuit, right? So if I come in and I replace this circuit, that means I have this circuit here. I can also take this resistor and I could say, well, this is only going to be one resistor. Here's my series resistance. And then what you're going to see here is that I then have this branch. So all of a sudden, the circuit is a lot easier because I've now isolated it, but I can also calculate any of the individual voltages here. So to give you a sense of this thing here, let's put these things together here. As an example, so I don't get too abstract here, consider that I have my circuit here. So I have some glob here, and I don't know what this circuit here, but what I do know is that I have a combination of resistors, sources, something like this here. And let's say this is my branch here. And so what I'm going to do here is I'm just going to give these guys some arbitrary values. I'm going to say this is 1 ohm, 2 ohm, 3 ohm. And I'm going to call this guy 6 volts, and I'll call this guy 12 volts. So the first thing that I note here is that all elements are in series. How do I know that all elements are series? Look at the connection. There's one connection between the 1 and the 6. There's one connection between the 6 and the 2, one connection between the 2 and the 12, and one connection between the 12 and the 3. Now, because they're in series, this means here is that we can move resistors and sources around. Why? Because series elements add. So that means here is that I want to take this circuit here and I want to redraw it. And the way I redraw this here is that I come in here and I'm going to say, okay, here's my circuit. So what I'm going to do here is I'm going to take all of these resistors and I'm going to move them so they're all right next to each other. So here's my 1 ohm, my 2 ohm, my 3 ohm. That's an equivalent of doing that. Now I can take my two sources and I can put them right next to each other. And so I have 6 volts here and I have 12 volts here. So then, because these guys are in series, you could see that the series resistance in this case is then, of course, 1 plus 2 plus 3, which gives you 6 ohm. So then I'm going to pick a direction here. And so when I focus on these guys right here, because these guys are in series, what this really tells me here is that this is going to be plus 6. I'm going to pick any direction that I want. So if I pick this direction right here, then I see the plus. And then when I come to the 12 volt, I see what? I see negative 12. So that means here I can replace this with the negative 6 volt. So what does the circuit really look like? In my mind then, I could keep it this ugly way over here, or I can reduce this thing to a series equivalent. So how do I reduce it? I know that this is a 6 ohm resistor. And then I have a source here. Now note, this tells me that I have a single source that looks like this here. According to our definition, the way I picked my path, this source is minus 6 volts. So what am I going to do? I'm going to switch the sign of this guy, and I'm going to go, this is plus minus, this is 6 volts, and that's my equivalent circuit right there. So look how I went from complicated to a much easier series equivalent. That's what I want you to do. That's what it means to be a branch to be series equivalent. Okay, let's go to the next part now. So the next part here is I want to talk about parallel equivalence. So is this, I hope this is, this is pretty disorganized here. I should have been a little bit more organized. Maybe if I do this type of thing to try to, I won't do this right now, but I'll organize it better before I post it. But I'm not changing anything that I wrote here. So here I go. Now we're going to talk about parallel.
Carlos,
Yes.
you mentioned that you had 4 characteristics. I
Did
only put
I?
down 3, I don't know.
Oh my gosh. You know what I did? I did it without writing it down. Okay, let me go back to the fourth, okay?
Okay, thank you.
Thank you for helping me out there. I skipped one. So let's go to the fourth one. So 4 here is that voltage sources, okay? So it says series voltage sources excuse me, add. Series voltage sources is add and all series current sources must be the same value. That's the fourth thing here. So, sorry about that. So let's go look at this thing here. So what you find here is that if I have a branch of sources, however signed, so this could be 1, this could be 2, this is Vn. If I have them in series, what I can do here is that I can take one of these sources and draw an equivalent of this thing here. So when I look at this guy, if I apply KVL, let's say that I come across here and I'm going to go KVL in this direction here. What you're going to see here is that this guy here is my open. So when I look at this open here, you could see that according to KVL, I'm going to go the first one because of my path. You could see that my path is coming here. I see what? I see a plus sign. So I'm going to get plus V1. Then I go to 2, and you could see as I go to 2, there's a minus sign there. So I'm going to write minus V2. And I can just keep going on with all of these sources here. And when I get to the very last one here, you could see that Vn is then going to give me a plus Vn, and that has to equal the voltage of the open, right? This has to be the voltage of the open according to KVL. Oh, I'm skipping a step. So look what I'm going to do here. So then if I come all the way around, I hit the open, and you could see that the open I've defined as negative of the polarity. I'm going to write this as minus V open, and that has to equal to 0. In other words, V open is then going to be the sum of all of these voltages, which will give me minus V1 plus V2 minus Vn. So that means if I define my polarity of this source, I'm going to get V open right here. So voltages in series add together. Current sources in series must have the same value. And so that means here, if I have a branch And let's say that I have multiple current sources. Maybe they look something like this, and I'll call this one I1, I2, I3. These current sources, I1, must then be equal to minus I2, which then must be equal to I3. If they do not have the same value, the current source will discharge to the lowest current value. And what happens when it discharges like this, what it does here is it damages it. And I know that you can't, how do I say this? I'm pretty sure you can't understand what I just said right here. And what I think I should do here is that I should come back and talk about this when we deal with parallel voltage sources. There, I can explain to you a little bit better what actually happens. So how about if I just wait a moment and then let me get to the parallel sources, and then I'll explain that. But that's the fourth one. Thanks, Morgan, for the help. Okay.
Yeah, no problem.
So let's go to the parallel ones now. So now we want to talk about parallel equivalence. Parallel equivalence is they're more work. And the reason why they're more work is that they have what do you call them? Their resistances add inversely, not directly. Okay, and that's really what the problem is here. So here we go. Our job is to identify the primary behavior of circuits. And once again, so the primary behavior, so parallel characteristics then come like this. One, parallel resistances add inversely. So the question is that how do they add inversely? What you find here is this here, that when you look at the resistance equation, when you add parallel resistors, what you're doing here is that you're adding areas instead of lengths here. So here, what you find here is that the area is inversely. So this means here that when you add parallel resistors, one is increasing, area instead, not length. So since the resistance is the inverse of parallel, then we say then R parallel is then the sum of their inverses. And you're going to see here is that there's a lot of tricks of how to calculate R parallel. And I'll show you these tricks. You know, maybe I should just show them to you right now. Okay. So there's some tricks in dealing with parallel resistors. and they go something, you know what, I think I'm going to wait because I really want to talk about the equivalent circuit a little bit more before I do this. Okay, the other thing that we know here is this. Parallel elements have the same voltages. Across them. In other words, that means that the voltage across resistor 1, across resistor 2, however many they are, must be the same as the source, or in our case, the branch voltage. So what do I mean by that? So let's go look at that. So I think this is a good time to go in and start to combine all of this here. Well, if I have a parallel circuit, and I have, let's say, a series of resistors. And in this case, I'm going to pick 3 resistors. 1, 2, 3. So what typically happens here is that I have one node. You can see that there's a node right here. And that's typically what we call the ground node. And then there's another node up here. So if the bottom of the power supply is 0, then the top node is V source. So you can see that each resistor has 2 potentials and therefore 1 voltage. So therefore, the voltage of 1, 2, and 3 in this case must be the same as the source. Okay, fine. So what does this really tells us here? Well, this tells me here is that I'm going to have 3 currents. There's a current going down here, which is 1, 2, 3, and this is our I source here. So they have the same voltages, but what we find here is that parallel elements divide the current. So what you're seeing here is that if I have a source current, it's going to split between resistors 1 and 2. And so if I apply KCL, so using KCL, what you're finding here is that the source current must be I1 plus I2 plus I3. But wait a minute, I know that each of these resistors has the same voltage. So I could come in here and I could do the following thing. I know that V1 over R1 is going to give me that, V2 over R2 and V3 over R3 is going to give me that. But since all of these voltages are the same, I can write it this way here. And so what you're seeing here is that according to our rules then, V source can be written then as 1 over R1, 1 over R2, 1 over R3 into the source current, which then tells us then that this is equivalent to rewriting this thing as what? An equivalent parallel resistance times I source. So I can rewrite this thing in this way here. So picture-wise, that means I can take this circuit which is 1, 2, and 3, and I can draw it equivalently by one parallel resistor that looks like this here. So that's what it means, that I can replace this thing in this way here. So, but the thing that I want to do here is that I want to show you this example to try to get you to start to think about what does it mean to be a parallel resistor. So what we want to do is we want to do this thing here, is that I now want to focus on two parallel resistors. And what I want to do here is that I want to show you some tricks here. Okay, so the first thing that we want to do here is that if I have 1 over R parallel, what this tells me here is that I have to have this guy right here. Now, if I solve for this thing algebraically, then this is going to be R1 times R2 divided by the sum of this thing. Please do yourself a favor, memorize this thing. Okay? Memorize this thing. What you're going to find here is this here. When we add, so when we add resistors in series, our series increases. When we add resistors in parallel, our series is. So that's one thing to think about. Another thing to think about is that RP is always less than the smallest resistor. So when you're doing a calculation, you should always remember these little guidelines. So what we want to do here is that I want to now go start looking at some simple examples about parallel resistors here. So
when you have more resistors in parallel, does it follow like R parallel is R1, R2, R3 over R1 plus R2 plus R3?
nope,
Just for 2.
it does not follow that, only for 2. And this is why I said I'm going to focus on what? 2 resistors here. Now, before I get caught up in just 2 resistors, what I want to do here is that I want to go in and I want to focus on some techniques here. And then you're going to see it's the 2 resistor one that becomes super, super, super important. Why? Because of textbook problems. Okay, so here's what I want you to pay attention to. So let's look at a series of examples here to get you to be really fast at looking at parallel resistors. So what people fail to realize that you can move resistors that are in parallel all the time. So imagine that I have a branch here now. And then I have a whole bunch of parallel resistors. So let's say that they look something like this here. So I'm going to say, I'm just going to draw a whole bunch of these. Let's say that I have 6 here. So I have 6 resistors, and look how I'm going to write them down. This is 9. Let's say this is 9, and this guy is 9. And then I'm just going to scatter a couple here. Let's say this is 2 ohms, this is 2 ohms, and then this is 5 ohms. Okay, so a lot of times people are going to say, well, let's calculate, because there's 6 of them. I'm going to say, so if you're going to go calculate this R parallel here, well, here, let me do the inverse of this thing. So if I go calculate R parallel, what you're going to do here is that you're probably going to say, oh, it's 9 plus 1/2 plus 1/9 plus 1/5 plus 1/2 plus 1/9. Well, note that you're adding things. So check this out. What you could have done right away in this circuit is that you want to manipulate these guys right from the get-go. In other words, check this out. Why couldn't you could do this instead? What you'll do here is that look at all the resistors. Well, for starters here, I'm going to move my 5 ohm right here. Why there? There's only one of these guys here. But now look at the 2 here. If you look at the 2, note that there's 2 of them. So what I'm going to immediately do here is that I'm going to come in and I'm going to combine these 2 ohm resistors right here. And then I'm going to come over here and I'm going to take my 9s, which are in 3. So this is 9, 9, 9. So what you're seeing here is that I can move resistors in a branch to make it easier for me to sort of like, make my calculations easier. So what I'm seeing here is, look at this. So I have 2 of 2 ohm resistors. I have 3 of 9 ohm resistors, and I have 1 over 5 ohm resistors. So immediately what I can do here is that I could take these resistors and write it as what? I could come over here and just say, well, my equivalent circuit is really what? Well, I have a 5. But I know that 2 over 2 is really 1, so I'm going to come over here and I'm going to say, I'm going to replace that as a 1 ohm resistor. And then this other resistor, because it's 3 over 9, this is a 1/3 ohm resistor. So you can see here is that this final resistive circuit that's parallel is much easier if I go in and I calculate the parallel resistance as what? 1/5, 1 ohm, 1/3 of an ohm. So if I then go and I do the calculation here, I could then say that RP for this case, if you do the numbers here, then gives you something like this here. My point is not so much the numbers, but that you can move parallel resistors here. Now, let's go to the tricks here. Okay? I want to go look at the tricks here. So the next example that I want to look at is that I want you to pay attention to resistors values. So what I'm going to focus on is that I'm going to focus on this relationship, that the resistance of parallel resistors is that, so I'm going to have a scenario like this here. So I have 2 resistors in parallel. So this is R1, this is R2. And what I'm interested in here is that I want to calculate the equivalent resistance of these 2 resistors here. Now, here's the thing. When you look at textbook problems, you'll find here that they do something kind of out there. They give you things in terms of equal resistors. One resistor's half of the other one, one's third, one's quarter, 1/5. And I want to show you some tricks of how to actually do this. Okay, so here's a 2 resistor trick. Okay, so let's say that R1 is equal to R2. So if R1 is equal to R2, then if I have 2 resistors in parallel, look how I write parallel. I put the parallel symbol. Then that means that this is then going to be R1 times R2 divided by the sum of the 2. But wait a minute, if they're equal, I can replace it by one of the resistors. So then this is going to be R1 squared divided by 2R1. So what am I going to get? I'm going to get 1/2. I'm going to get half the value of one of the resistors. So in other words, if I have a resistor that's a 4 ohm, and I have another resistor that's a 4 ohm, you can see here that I can immediately take those two resistors and I can replace this guy by half of this, which is 2 ohms. So if you see two resistors like that, then you should immediately reduce one of the resistors by a factor of half. But then there's another situation. Check this out. What happens if R1 is half of R2? What does the equivalent resistance look like now? Check this out. This tells me, according to the equivalent resistance of these two resistors, that it's going to look like what? It's going to be R1, and then I'm going to have R2, R1 plus R2. Now I'm going to plug that guy in. So look what I get. I'm going to replace. So now what this tells me here is that R2 here is the larger resistor. So you want to write everything in terms of the larger resistor. Look what happens now. So then I'm going to take R1 and I'm going to write 1/2. Then I'm going to get R2 squared. And then I'm going to get 1/2 R2 plus R2. So look what you get now. Well, for starters here, I can bring that 2 down and I could cancel one of the R2s. So then what I'm going to get here is I'm going to get 1 plus 2 divided by R2. In other words, this is 1/3 of the larger resistor value. Look what happens here. See if you can see the pattern. If I have two resistors that are equal, the equivalent resistor is 1/2. If I have that one of the resistors is half the large as the other one, the equivalent resistance is 1/3. So in other words, if I have a resistor that looks like this, let's say this is 6 and the other one is 12 ohms. See how this is half of that value? So according to this rule here, I can take this and I'm going to apply this thing right here. This tells me that I take 1/3 the value times what? The larger resistor value, which gives me 4 ohms. So you could immediately take that resistor and reduce it instantly. So then the pattern continues now. What happens if I have a resistor that's now 1/3 of R2? Remember, R2 is what? The larger resistor. You know what you're going to get? Look at the pattern. Look at that. 2, 3. The next one is going to be 4. That means when I go and I calculate the equivalent of these guys, I'm going to get 1/4 the value of the larger resistor. So if I have a resistor circuit that looks like this, 4 ohms, and then the other one is 12 ohms. You could see that 12 is 3 times larger. That means I'm going to come in here and I'm going to replace that resistor. What am I going to do it with? 1/4 the largest value. So therefore, this is automatically 3 ohms. So you're seeing here that the value then goes, look at the value now, right? It's 1/2, 3, 4. So now you can just start writing these down here. Look at this. That tells me that the R equivalent is then going to be what? 1/5 the value, 1/6 the value, etc. So this allows you to take certain circuits and immediately get the resistance like really fast. So here's an example then. So suppose that I have a branch that looks something like this. So I have a 6, 12, and a 4. I want this guy like this. What is the equivalent resistor? So note that's 3. Most textbooks would tell you to go do what? They go add them the inverses, right? Most textbooks are going to say, oh, you want R equivalent? Go add this. And you know what I'm saying? Asinine. That's what I'm saying. So what do? You focus on two resistors. So check it out. Look at these two resistors right here. What do I see? Look at that. They're half to each other. So in other words, in my mind, I'm going, well, that's half. Well, half of 12 is going to be what? Is going to be 6, right? So half of this guy tells me that I take the biggest resistor. I'm sorry, it's half. And I'm going to divide this by 3. So all of a sudden, this guy here, which is this guy right here, is now what? It's 6 parallel to 12. So you should immediately say, divide by 3, I'm going to get 4 ohms. And so now we have what? We have another 4 ohm. So now I have a 4 ohm and 4 ohm in parallel. And if I focus on these two now, then you could see that I then take my last resistor and I go, well, I got to divide it by half. So this is 2 ohm. So all of a sudden, you're taking these 3 resistors and you're instantly putting them, reducing them very, very, very quickly here. Okay, so that deals with resistors and dealing with parallel resistance. So the last thing that we want to focus on now is that, damn, we're not going to have enough time.
Can you scroll up one line for a half second?
Yeah, the last thing that we're going to deal with is that I was going to derive the current divider rule. And I think I have 3 minutes left. I'm not going to have enough time. So you know what I'm going to do? I'm going to stop right here. Okay. So yeah, I'm cutting this thing short. I should be docked for pay here, but as soon as I write just a tiny bit, I'm going to end up stopping. So on Monday, I will pick up the current divider rule and derive it from scratch. Okay, and then we're going to start a whole bunch of examples. I think I got 6 or 7 examples. And I'm literally going to ask you, okay, here's my circuit. Does it behave series-like or is it parallel-like? Then there's all those lists of things that you got to go after. Okay, remember, you got a quiz today and good luck. Okay, I'll see you guys later, huh? I'll see you Friday, people, in lab on Friday.
Quick question.
Okay, bye-bye.
Can you send us the can we access the examples ahead of time so that we already have them like written out so that we can follow better?
Yeah,
they're online.
Okay, they're already on Canvas.
Yeah. I mean, let me show you where, just so that you can see here. So if you go, right?
Lecture 2 resistor.
If you go to my lecture notes, right? Look, you click on the lecture, and every one has not only my lecture notes, but look at the examples.
Oh, gotcha. Perfect. Thank you.
Yeah, so if you go to any of the modules, you'll see that that's exactly what it is. If you go to the second one, you'll see that it's the exact same thing. The whole semester set up this way.
Perfect. Most teachers don't put them out ahead of time. Thank you.
No, dude, I have the whole semester up already. Okay,
Carlos is not
I'll see
like
you guys later.
Later.
Have a good one, Carlos.
Okay, later on.
Hey, Carlos.